Getting to the end here of chapter 14. We're working pretty much the last example. So last week, I believe we went through parts A, B, and C here in this titration. Again, just to remind everybody, we're doing here a titration of a weak acid with a strong base. So once again, we are adding the strong base from the burette to the weak acid that's in your flask or your beaker. We basically did kind of at the initial beginning part of the titration before we add any sodium hydroxide. All we have again was a weak acid. So to figure out the pH, it really is just a Ka type problem where you can do an ice table. You could use the initial molarity there again, because you have not added any sodium hydroxide at that point. So you don't have to worry about moles or anything like that. That would be like we did an ice table where you use X's. You can make your assumption, which again, a good reminder, you should check it because I believe again, in this case, it did not work. The assumption here on part A, and you solve for X, which is the H plus concentration. And then you obviously get the pH. Part B here was before the equivalence point. So again, we know we're before the equivalence point. When we do our ice table, which we do need to do the reaction between obviously HNO2 in this example and sodium hydroxide. It does need to be done in moles because we are adding obviously volume at this point. When we look at the ice table, as we saw, which we have right here, we again know we are before the equivalence point because again, the moles of what we are adding is less than the moles that what we are starting with. So that definitely means you're before that equivalence point. Because at the equivalence point, the moles should be equal, obviously. That also means that the sodium hydroxide should be the change here, and that's what we did. Remember that it is really good practice to convert back to molarity after the first ice table. And again, we would want to do that with our total volume that's been added, along with obviously the volume of the acid in this example here that we started with. And that's where we got the 180 milliliters at that point. At this point, you will always, in this type of titration, pretty much end up with a buffer. And that means we could go into our Henderson-Hasselbalch equation like we did, and obviously get our pH, in this case, of 3.95. Also, the pH is rising, which also does make sense since we're adding base, obviously, in our titration here. So it should start to go up. As we approach the equivalence point, or get to the equivalence point, again, we do see that sharp rise in the pH. And when we do reach the equivalence point, that means that we should have equal moles of our acid and base in this titration. And that's what we do see here. We end up with exactly the same amount of moles, which is basically your definition of the equivalence point. We also talked last time and a number of times before that, you know, sometimes they will not tell you the volume to reach the equivalence point, much like in this problem here. So there are a few different ways. Again, you can sort of quickly determine that. Again, M1V1 equals M2V2, as long as it's a one-to-one relationship between the acid and the base, that's good to go. Again, because you do know what the moles should be at this point, you would have the moles, and you obviously would have the molarity here of the sodium hydroxide. So you could use just the molarity equation and figure out how much volume that would be. So again, there's a couple different ways to sort of get yourself there in terms of the total volume. Once we do, we see what we typically will see occur here at the equivalence point in this type of titration is the acid, the weak acid and the strong base here is completely used up, as we can see here at the equivalence point part. But what we are left with is a salt, and this salt will always go through hydrolysis because basically it's a weak acid involved, and it comes from that weak acid. So in this case, it is the NO2 minus that will go through hydrolysis and react with water. So it does require a second ice table. Really, the first ice table was to figure out the concentration of your salt so that you could do the second ice table. Once you do that, the salt here is going to act as a base because it does come from a weak acid. So it will act as a base, which means it will accept the H plus. And as we talked about, obviously, common sense should prevail here. It does not have an H to give, so it cannot give an H. So it can only obviously accept an H in this case. When we do that, we will form hydroxide, which again means we know that it is going to be basic here with our pH. We also know that we should use a Kb, which again, in this problem, we probably have just a Ka given to us. So we do need to do that kind of Kw flip of it to a Kb value. And once we solve for X in this case, it will actually equal the hydroxide concentration, which means again, you could get the POH first and then to the pH. And here, as we would expect, 8.02 would be our pH that we got there. Any questions on those parts that we did last time? So what is left is clearly, since we just did the equivalence point, we are going to be past the equivalence point at this point. So we're going to add 105 milliliters of base. So let us take a look at that. So when 105 milliliters of our 0.1 molar sodium hydroxide is added to our 100 milliliters of our 0.1 molar nitrous acid. So once again, obviously we're in our titration, so we do need to have our equation, and that would be the same one we've been using, which is our HNO2 plus some sodium hydroxide, giving us our NaNO2 and our water here. Now, in this case, obviously we need moles. So initially here, we should start with the same number of moles we had on the other one. So that's 0.1 times 0.1 gets us 0.01 moles. Our sodium hydroxide 0.105 times 0.1 gives us 0.0105 moles and 0 here. Once again, this is what we are starting with. This is what we're adding. So if you didn't have perhaps the benefit of the previous parts of this problem, you can know that you are past the equivalence point by looking at the moles here versus the moles here. And obviously we have more moles of what we are adding than what we're starting with. So that definitely tells us we are past the equivalence point. So that also means at this point, we really have excess amount of sodium hydroxide that we're adding. The limiting reagent here would be the HNO2, and that would be our change, which would be minus 0.0, minus 0.01, and plus 0.01 here, which means when we reach equilibrium, we will zero out our nitrous acid. We will then end up with 0.0005 moles and 0.01 moles at that point. Total volume at this point is 100 that we started with, 105 that we added. That is a total volume of 205 milliliters. So dividing this out by 0.205 liters, we'll convert these guys back to molarity here, and that would get us 0.205. 0.00244 and 0.01 divided by 0.205, 0.0488 molar. So once again, at this point, if you're not sure what is going on, you could use your ICE table to help you. We do have obviously our sodium nitrite and our sodium hydroxide. Once again here, hopefully you can recognize these two things are not a buffer. They are not related to each other, even though you got two numbers. We do have obviously the salt, like we saw at the equivalence point, that will go through hydrolysis and act as a base. But much like we did and talked about at this point, we have obviously a much stronger base happening here. And because of that, at this point in the titration, we will ignore really the contribution from the salt, as the sodium hydroxide, as we talked about, pretty much just needs to go for a swim and it will produce hydroxide and change the pH and be the major contributor. Again, the salt there has got to go find some water, do a little reaction. It's probably not going to generate as much hydroxide. So because of that, this obviously would equal our hydroxide concentration. which means we could calculate the pOH, which would be minus the log of 0.00244 and 0.00244 gets us a pOH of 2.61. Once again, if you for some reason thought this was the pH, it should definitely not make sense to you at this point because that is not a basic pH. So we could convert it obviously into a pH here by subtracting. And if we do that there, we got like an 1139, which definitely is basic and kind of what we would expect to happen here after the equivalence point, really with not a ton of volume added afterwards. We do see a pretty big jump there from like a pH of 8 at the equivalence point, right, to kind of a pH here of 11.39. Any questions on that part of the calculation there? Question on titration calculations in general. As we talked about, it's really important first off to sort of identify what type of titration you're dealing with. And if you could sort of figure out where you are in that titration curve, it can make it really easier or a little bit easier to do the calculation part, because again, you really should know how it turns out and sort of what calculations and what stuff that you should end up having really before you even actually do the calculation. So I would actually recommend, as I mentioned, to take a moment, try to figure out where you're at, think about the type of titration. And again, that should hopefully focus you on the type of calculation that you should do. Any questions on any of that there? All right, so the last thing we're going to talk about in this chapter, finally coming to an end, is acid-base indicators. So obviously when we do a titration, one of the things when we do a typical titration, maybe not so much in a titration curve type of titration, but a titration like you've done in Chem 50 and so forth, we want sort of a visual representation of when the reaction is sort of complete. And most people consider sort of that reaction complete at the equivalence point. And again, that's the point where we have exact amounts of moles of acid and base together. So we can use an indicator to help us do that. Indicators basically work over a pH range. So they're really specific for a actual pH range. They are kind of considered like a weak acid. This is basically an indicator that has the proton on it, kind of like the weak acid version of the indicator. And this is kind of like the basic version of the indicator when it loses its H+ sort of in solution. Now, in terms of the ratio of sort of the protonated form of the indicator to the deprotonated form, if it's sort of greater than or equal to sort of 10, we will see the color in sort of the acidic solution. And if it's less than 10, we'll kind of see the base color. Each indicator typically has a color kind of in the acidic and basic range. And what that means is over whatever pH range it works for. So for example, phenolphthalein is like 8.3 to 10. And sort of in the 8.3 range, which would be considered like the acidic range there for this indicator, if you will, it is colorless. And then obviously, as we know, it gradually turns to pink as you kind of head to a pH of 10. You can see here crystal violet kind of starts at a yellow, kind of rolls to a green, and then in its sort of basic pH part of its range, or the higher part of its range, it turns to more blue color. Again, you can see some other ones here on this list as well. We got our bromophenol blue, which actually is, our methyl orange here, which is red to yellow. It kind of turns. The goal of picking the proper indicator is to pick one where you could see an actual color change occur near your equivalence point. So you do want an indicator that will actually change color near that equivalence point. So that will give you that visualization that you should stop the titration. That's why phenolphthalein is used a lot, especially with the one like you did before, where you probably did vinegar and some sodium hydroxide. The vinegar is basically acetic acid, which is basically a weak acid and a strong base. Equivalence point is probably in this range right about there. 8 point something is probably the equivalence point. And that's why they yelled at you to always get it to the lightest color of pink that you could get. And that's because it would put you ideally, near the equivalence point when you stop. If you went again too dark pink, you may be way past that equivalence point. We also talked about that, if you're kind of careful as you're doing your titration, even if you miss it by a drop or two, volume-wise, you'll be okay because it does go vertical at the equivalence point. But again, if you weren't very careful and again, just opened it up and it turned really dark pink, you're not really sure exactly where you'd be at. Yeah. There are the pHs, yeah. So again, that's why you typically when you use phenolphthalein, they kind of yell at you, go the lightest color pink, because that is somewhere near the equivalence point pH. And again, because the titration curve, as we've talked about, does really go vertical, even though the pH, at the equivalence point is here, like basic for this type of titration, neutral for like HCl and so forth. Even if you stop somewhere in the 8-ish range up here, again, volume wise, you're probably fairly close to where the volume should be. There were no, maybe a little bit off in terms of the pH. Again, if you're not careful and you just overshoot it a lot, you could also have that really dark pink over here, and you're clearly way far away from your equivalence point as well. So they do help us choose. We do want to choose one that would work appropriately for the equivalence point. Because you know how to do calculations, you could actually do a theoretical calculation if you know the molarity and everything that you're using in a titration to have an idea as to what you would expect the pH to be at the equivalence point. And you could really narrow in a very good indicator that would change in the appropriate sort of pH range. Would we want to choose something like crystal violet for that type of titration that we just talked about? The answer is not so much, because right around a pH of 1 is going to change color and going to sit at that color probably for the rest of the day there for you. So you're not going to have obviously a visual representation where you should stop. That is again why we would want to use something like phenolphthalein in this type of titration. Any questions on that there? All right, so looking at this list here, here's some indicators. Which indicator would be a good one for kind of like the titration we just talked about and did the calculation for? Take a second, see what you come up. We just used in the previous problem. KOH is what type of base? It is a strong base. So again, we were adding the base to the acid here. What we should know is when we get to that equivalence point, the pH should be acidic, basic, or neutral. It should be basic always in this type of titration. Again, because we are going to have, just like in the example we just did, a salt that will go through hydrolysis and produce hydroxide. So we should expect it to be basic. What that means, if we look at our list here, that is definitely an acidic indicator. It will turn color in between 1.2 and 2.8, which is way too soon for us to use. Obviously, same thing here. That's too soon. That's too soon. This is going to turn color again between a pH of 4.2 and 6, which means that is again a little bit too soon. That one is too soon. Clearly, this one you might say does get into the basic range, but frankly, at that point, it probably has already turned color. So again, that's going to be a little bit too soon for you. So that does leave us kind of these last two, which kind of cover a nice little basic sort of range here. And again, like I said, you could probably narrow it down by doing sort of a theoretical calculation and choose which one would be good. If it's definitely pretty basic or getting into that 8-ish range, probably phenolphthalein is what you would want to choose. But if it's just sort of basic at the equivalence point, maybe that guy would be a better choice. So out of this list, those last two would obviously be probably your best choice. Any questions on that there? Any questions on titrations or anything else we talked about in this chapter here? All right, that is this chapter, finally, the end of it. All right. Like I said, we're going to go off to 15. Just give me a second here to punch it up. So in chapter 15, it's not too long of a chapter, but does cover a couple of things that, again, do give students a hard time. We're going to talk about two other types of equilibriums here. We're going to talk about Ksp, which is the solubility product. And we'll talk about Kf, which is the formation constant. This guy, as you can imagine, deals with sort of solubility. This guy, as we will talk about, deals with what are referred to as complex ions. So these are two types of equilibrium constants that deal with these two types of things. And they can sort of intermingle, if you will, as we'll see at the end here. But ultimately, as we will see, they really are still just equilibrium constants. So we do pretty similar types of calculations. There's a few sort of tweaks that we sort of do along the way. So let's start with Ksp. Ksp is what is known as the solubility product. It is typically the equilibrium constant that we use for things that are insoluble. So this is kind of the guy that we use for things that we typically think of as being insoluble based on solubility rules. You remember solubility rules, right? Things like nitrate are soluble in everything. Chloride, bromide, iodine are soluble in everything except for lead, mercury, and silver, and so forth. So if it's been a while for the solubility rules, you may want to take a peek at them again to refresh your memory. But the good news is you could probably safely figure out most things, even if you don't have a good understanding of the solubility rules in this chapter. But it can be very sort of helpful. So one of the things with Ksp type of things, because they really are for guys that are insoluble, a couple of things always sort of occur. And that is when you write the reaction for Ksp type problems, it always ends up like we see here with this guy. And what I mean by that is on the reactant side, it's always the solid guy. And on the product side, it's always the aqueous ions, basically. So your aqueous ions always end up on the product side. Solid is always usually on the reactant side. And what that means is when we write an equilibrium expression, it is products over reactants. And one of the things we never put in there, right, is solids. So typically our Ksp sort of expression is only the products because the reactants are always going to be solid here. So that's what we see here when we look at silver chloride, which again is a white solid that you get when silver and chloride come together based on solubility rules. That is something that is insoluble. And if we write the equilibrium expression or the Ksp expression, as we can see, it is just our product. So it's the concentration of silver ion times the concentration of chloride. Now we do exactly the same thing we do with a normal equilibrium, which means if there is a coefficient, we also use it as the exponent. So when you have something like magnesium fluoride, it will break apart into 1 magnesium and 2 fluorides. So once again, we do need to take that 2 into account when we write the equilibrium expression for it. And same thing here, silver carbonate, we got a couple of silvers. So once again, we want to make sure that we don't forget to take that into account. And calcium phosphate, 3 calciums, 2 phosphate. Again, taking those into account when we write our Ksp expressions. Also, because these guys are typically for things that are insoluble, would you expect the Ksp values to be large values or small values? So let's talk it over. If these are things that are typically insoluble, that means they are typically going to be solids. Which side of the equation has solids? Reactant side. So in order to have more reactants, you need a large K or a small K? A small value of K means that you have more reactants, right? Reactants over product, or products over reactants, I'm sorry. Products over reactants means more reactants, smaller K, right? Larger K, more products. So Ksp guys, because of that, typically are very small values. Again, because basically we're taking products over reactants. If we have mainly reactants, going to bring our Ksp value down. Now, we could also use a calculation that we've done before in a previous chapter to help us decide whether or not we would get a precipitate form. And one of the things that we will learn in this chapter and that we will see in this chapter is solubility rules are not always correct in 100% of the situations. So sometimes when we look at those solubility rules or taught those solubility rules, we always think it is always the case, no matter what the situation, that if you put these two guys together, you'll get a solid. And that's not necessarily true. There's a lot of factors that affect whether or not you will see a solid form. Couple of things that affect sort of solubility is things like pH, things like common ion, and things like concentration. So if any of those things are incorrect, even though solubility rules tell us it should get solid, you may not actually see the solid form. So there's a lot of factors that actually affect solubility. One that helps us sort of figure it out is Q. And a reminder that Q is the reaction quotient that we saw in like the opening or second chapter there. A, P or K, and that is still our products over our reactants, right? So we calculate Q the exact same way, which means in this case, because we're dealing with insoluble guys, same thing will happen. It's pretty much just going to be our products that are going to happen here when you calculate Q. If you calculate Q, it is less than the Ksp, kind of pointing opposite of that arrow. It means that you would expect no precipitate to form. And when I say opposite of that arrow, it's pointing to the product side, which is no precipitate. And you would have what is known as an unsaturated solution. An unsaturated solution, yeah, question? Yeah. Are you asking what an unsaturated solution is? They will not. So much like what we use, well, they may be. I won't say they won't be, but it's possible they could be the same number. It's possible it will be greater than or less than. So remember that Q is a reaction quotient, which basically is calculated in a situation. Originally, we talked about it, that we were not sure if we were at equilibrium and which way we need to go to reach equilibrium is what we typically would use Q for. And it's kind of the same idea here. Technically, if we're not at equilibrium, we're going to go one way or the other, which means either we will have a solid or not a solid in this particular case. So it is potential it could equal each other, but based on sort of the concentrations that you're putting together, it may end up being larger or smaller than the actual Ksp value.
It's products over reactants regardless, but Q is just at equilibrium, is that correct?
Q helps you determine whether or not technically you're kind of at equilibrium. And if you're not at equilibrium, what it also helps you decide is which way you need to go to reach equilibrium is basically what Q kind of tells you. And in this application of Q, what it will tell you is whether or not you would expect sort of a solid to form if you kind of threw these ions together. Because based on solubility rules, it will say, yes, you should get a solid. But again, depending on the concentrations that you're putting them together is a very major factor in terms of whether or not you would see the solid actually form. And that's where Q would kind of come into this application. Again, that's how you could get either kind of lower or higher than the Ksp value. Yeah. Question? They're good? Okay. So an unsaturated solution is, again, a solution where basically, you can dissolve solid in and it will continue to dissolve. It will continue to dissolve until you hit basically the middle there, which is a saturated solution. And that is when Q could equal Ksp. A saturated solution is a solution where you hit pretty much the maximum amount of solid that would dissolve at a given temperature. And basically, if you add any more solid, you're not going to get anything to dissolve. And that will then push you over to the last situation, which is Q is less than the Ksp, which means it would point to the other side, which is the solid side. And in this case, you would actually have a supersaturated solution, which means you definitely would expect a precipitate to form. Technically speaking, a saturated solution is, if you're right dead on that, you probably would not have a solid form unless you added one more grain or something of it together. Then you would start to see sort of a solid form at that point. So we can use Q, and Q will help us in terms of concentration, which is, again, a major sort of factor as to whether or not you actually will see that solid form based on solubility rules. And we'll get back to Q in just a bit. Here's a table from your book, which clearly you could see all these values, but basically they are all very small values, like that is to the minus 39, you know, minus 20 something there. So those are really, really small values, which means for the most part, everybody's hanging out on the reactant side. But even things that are technically insoluble have some degree of solubility. So a little bit of it will still break apart because it is an equilibrium. So you'll have a little bit of it in sort of its ion form, but a vast majority of it obviously will sort of precipitate out in terms of its solid. In case you needed more. So when we do sort of Ksp problems, there's sort of two things that we a lot of times will kind of look at. One is what is referred to as the molar solubility, and that really is just the molarity. And that is how many moles of that solute you can dissolve in 1 liter of a solution. Sometimes we're interested though in a more maybe useful type number, which is the sometimes referred to just as the solubility, which is the grams per liter. So how many grams you could dissolve in a liter of solution. So in these type of problems, there's sort of two types of problems that we come across. Technically speaking, one requires an ice table, one doesn't really require an ice table, but you can do ice tables actually for both of them, which may be helpful to you. The first type is you're given the solubility of the compound. So what you would want to do in that case is figure out the molar solubility of each of the ions, put it into the Ksp expression, and then you could actually solve for the Ksp. So this would be a problem where you're asked to solve for the Ksp. The other type of problem, and by the way, that first type of problem there technically doesn't require you to kind of do an ice table, but it may be helpful to do. The second type of problem is you're just given the Ksp, and that's pretty much it, nothing else. And this way typically does require an ice table to be used. And you would use the ice table kind of like a normal ice table we've done before. When you solve for it, you would be solving for what is known as the molar solubility of that particular compound, which then you could obviously convert to grams per liter. By the way, if we have the molar solubility and we want the solubility in grams per liter, what do we use to go between those two? Yeah, you use the molar mass from the periodic table to go between those, right? Because that is grams per mole. Moles cancel, grams per liter, right? Is left over. So sometimes you do need to use sort of the molar mass, obviously, to bridge that sort of moles per liter to grams per liter here. So let's take a look at one here together just to kind of see how one of these works. The solubility of silver phosphate, dramatic pause between the silver and the 3 there. 25 degrees Celsius is 1.6 times 10 to the minus 5 moles per liter. What is the Ksp for silver phosphate? So this is one technically that you don't necessarily have to do an ice table, but I'm going to do the ice table to, yeah. What's that? What's that? The three here? No, it should be, I don't know, I got spaced out here. PowerPoint did something, but it should be this, yeah. So we don't necessarily have to do an ice table here, but I'm going to do it in this problem and show you why it might be beneficial for you and also help you understand how to do ice tables for ones, obviously, that you need to do. So if we took more of an ice table approach, we would do our silver phosphate, which we know will be a solid. And you may ask, how do I know it's going to be a solid? Because it asked me for the Ksp, so that's a pretty good hint that it should be a solid. This is going to break apart into 3 silver ions and a phosphate ion here. The Ksp expression for this guy would be the silver that needs to be cubed and the phosphate. Again, here our reactants are solid, so they are not included in this. So what we would want to do is sort of approach this question. That's okay. What's up? No, we're not doing any pH meter. What's that?
That bracelet in your corner.
Okay, no, we're good. Thank you very much. So if we want to do this as a ice table here, what we're going to do is set it up like normal. So we will have our initial. And again, because the reactant side here is solid, we're not going to even play with it. So we're just going to go to our product side and start with zeros. Now, slightly different in these type of problems is they kind of use a different letter when they do these KSP type of guys. We're going to do our change, which will be plus, still need to do the coefficient. So that's going to be 3s and plus s. So a lot of times in these, we use the letter S, and what S stands for is the molar solubility. So when you solve for S in this table, you're solving for the molar solubility, which means that you are solving for the molarity here. Now, bringing this down gives us 3s and s. First off, any questions on the ice table? So very similar to a normal ice table, except again, here we kind of use a different letter, which stands for the molar solubility. And again, we pretty much leave the left-hand side there alone because it is a solid. Just like normal, we would go into our KSP expression, right? And instead of solving for X here, we would solve for S. So putting that into our KSP expression, it is going to be 3s cubed times S. Now, if it was a different type of problem where we had the KSP value, we would just solve for S in this case. But in this problem, we're actually looking for what the KSP value is. And that is where this number would come into play. This is the solubility of this compound in moles per liter, which means that this guy is S. That is the molar solubility. So to figure out what our KSP would be, since we already know what S is, we would take 3 times 1.6 times 10 to the minus 5. We want to also still make sure to cube it, times 1.6 times 10 to the minus 5. And if we do that here, hope for the best, 3 times 1.6 minus 5. Then we're going to cube it and then times it by 1.6 exponent minus 5. Will give us a KSP value of 1.8 times 10 to the minus 18. Is that a large value or a small value? A small value, which again is what we would expect here, since this is something that is typically insoluble and should hang up on the reactant side. So this is typically how sort of a KSP table looks like and sort of how you work through it. And again, like I said, the variation would be you're just given the KSP. So obviously you would have the number and you could solve for S, which would give you the molar solubility. Now, the reason why you might want to still do an ice table on this one is people always run into this internal argument with themselves, which is, I know it's a 3 and I know I'm multiplying by 3, but do I still need to cube it as well? So people always end up deciding I should do one and not the other. And here it will sort of help you visualize that you should be multiplying by 3 and also cubing it. Again, it's a very common thing. People go like, I did it once, why do I have to still cube it? If you didn't want to do the ice table and you understand molarities, which is, you know, if this thing was 1.6 times 10 to the minus 5, it is a 1 to 3 relationship for the silver. So you just go 3 times 1.6 to the minus 5. It's a 1 to 1 relationship between the phosphate, which would be 1.6 times 10 to the minus 5. Now you have basically both of these numbers, and you could go right into the KSP expression, which is essentially what the ice table is walking you through. But again, if you don't understand that relationship or not sure how to do it correctly, again, the ice table can kind of help you visualize what you're doing. Because again, this part right here is basically this, and obviously this is this. So you don't necessarily have to do an ice table on these if you understand the relationship between the molarity of the whole compound and the ions, and you could kind of go right into the Ksp expression to do it. Or again, you could do the ice table to help you visualize it. Any questions on that there? All right, I did one. Why don't you do one here? What is the solubility of silver chloride in grams per liter, which is basically the solubility of it in water? So take a couple minutes, see what you come up with. Once again here, you do need to do an ice table on this one for sure. We're only given the Ksp value. That also tells us if you weren't sure that the silver chloride should be a solid. So we will start with our equation here, which is our silver chloride, breaking apart into silver plus chloride here. Ksp expression here would be the concentration of silver times the chloride concentration. So we have no option but to do an ice table. So 0, 0. Again, the change here would be plus S, as each of the coefficients are 1. At equilibrium here, we would have S and S at this point. Any questions on the table? All right, so just like we would do with X, we're going to put this into our Ksp expression, and that would give us the Ksp is equal to S times S, which equals 1.6 times 10 to the minus 10. That's going to give us an S squared is equal to 1.6 times 10 to the minus 10. Doing a little square root action on that there. If I could find it on this calculator, it is somewhere. Where's my square root? There it is. 1.6 exponent minus 10. Going to give us a S of, we'll call it 1.3 times 10 minus 5. Yeah. This S again represents the molar solubility. So this is really moles per liter here. And this S, you may be saying, isn't the S silver and isn't it chloride? Is it silver chloride together? And the answer is yes, because if you do a one-to-one relationship backwards, you get the same molarity between any of these guys. So typically speaking, if you solve for S, that is the molar solubility of the whole thing. Is typically what you're solving for. So to go from obviously the molar solubility to grams per liter, we need the molar mass there. So we're just going to add those guys together basically. And that gets us, looks like a 143.4 grams per mole would be silver chloride's molar mass. So the last part here would be 1.3 times 10 to the minus 5 moles per liter, using the molar mass of silver chloride, which is 143.4 grams per mole of silver chloride. Moles will cancel, ends up with approximately 0.0019 grams per liter. Yourself any questions on that calculation? Is that a lot of grams that you could dissolve in a liter of solutions? That is not. That's like 0.002 grams you could put in 1,000 milliliters of water to get it to dissolve, which is why we typically think of silver chloride as being insoluble. But here it also shows that even it being pretty much insoluble, there's still a little bit of it that will dissolve, and it's a very, very small amount. Any questions on any of that there? All right, so give this one a go. Again, the spacing. This is aluminum. It's dramatic pausing. That's what that is, I think. Aluminum 3+. All right, we'll calculate the concentration of aluminum 3+ in a aluminum hydroxide. It has a Ksp of 2 times 10 to the minus 32. We're just given the Ksp, so that should tell us some ice table. Also should tell us our aluminum hydroxide here will be a solid. When it breaks apart, we will get an aluminum that has a +3 charge, and we'll get a few of the hydroxides there that have -1 charge. Our Ksp in this case would be the aluminum times the hydroxide, and we do need to make sure we cube it because of the 3 that is there. So we will go through here. So we're going to 0 up initially. Our change will be plus S. And again, the coefficient, we want to make sure we also take into account there as well. So that should be plus 3S. That means at equilibrium here, that should be S and 3S. Any questions so far? Putting that into our Ksp expression gives us S times 3S. And once again, making sure we cube it is equal to our 2 times 10 to the minus 32. That gives us a 27 S to the 4th is equal to 2 times 10 to the minus 32. You want to make sure you cube the S, but most people will miss the cubing of the 3 there. So 3 times 3 is 9, times 3 is 27. So that's an important one. Oftentimes missed. People kind of take care of the S, but not the number. That means we're going to divide our 27 to the other side there. And that will give us a 2 to the 32 divided by 27. That gives us an S to the 4th that is equal to 7.41 times 10 to the minus 34. We want to take the 4th root here of that. And if you're not sure how to do that on your calculator, you basically take the number, hit the caret, go 1 divided by 4 in parentheses. We'll do the 4th root for you. 1 divided by 3 would do the cube root. 1 divided by 2 would do the square root of it. So you could do that move if you don't have a button, which you might not. So we're going to do that. 1 divided by 4 gets us an S value of 5.2 times 10 to the minus 9 molar. Or if you have just a calculator that's not in scientific notation, you probably got something like a bunch of zeros and a 5 at dead end or at the end of your calculator. And again, it should be fine as well. That is, since in this case, we are looking for the molar solubility, or really the solubility, the concentration, which is basically the molar solubility of aluminum. Since that does equal S, that obviously would be our answer. If I wanted the concentration of hydroxide at equilibrium, what should I do with that number? Actually, I multiply it by 3, right? So I could take 3 times that number, and that would give me the hydroxide concentration at equilibrium. That is also the molar solubility of this guy, of aluminum hydroxide in water, basically, which you can use the molar mass of aluminum hydroxide and convert it to, how many grams per liter that would be as well. Any questions on any part of that? And again, I would say the common errors is, I did the 3, do I need to cube it? And also with the cubing part, not actually taking the number and cubing it as well. All right. So let's talk about kind of using the Ksp values to help us determine solubility and what would be maybe more soluble, what would be maybe less soluble, just by looking at the Ksp values. So when we look at our Ksp reactions, as we talked about, we pretty much have solid on the left-hand side and aqueous ions on the right-hand side in these type of reactions. So you can take the Ksp values and use them to help you decide which one would be more soluble or less soluble based on the Ksp values in only a very specific situation. And that specific situation is right here when you have the same number of ions. So if you look at silver iodide, it produces a silver ion plus an iodide ion. That is a grand total of 2. If you take copper 1 iodide, it produces a copper 1 ion and an iodide, also 2. And calcium sulfate gets you 1 calcium and 1 sulfate, which is 2 ions. In a case, if you're trying to compare solubilities of things that produce the same number of ions, you can use the Ksp values directly to do that. The one that has the larger K value Would it be more soluble or less soluble? Larger K value should be more soluble. Again, larger K value means more products. Product side is always the aqueous ions, so it would be more soluble. What that means is if you had two guys in solution and you want to compare the Ksp values, the one with the larger Ksp value should stay in solution longer. The guy with the smaller Ksp value should actually precipitate out of solution first or quicker than that guy would. Now, this is only can be done in a specific example like this, where we're comparing basically apples to apples, 2 ions to 2 ions, or 3 ions to 3 ions. Again, calcium sulfate would actually have the larger one than silver iodide. Now, when we get to a situation like what we see here, when we look at these 3 guys and we want to compare the Ksp values, we cannot do it directly, because when we look at copper 2 sulfate, you get a copper 2 and a sulfate, which is 2 ions. If you look at silver sulfide, you get 2 silvers and a sulfide, which is obviously 3 ions, right? 2 ions. And this guy, you get 5 ions on the bottom. You can't do that just based on the ice table, right? This guy's going to be like S squared. This guy is going to be like what we had a second ago, kind of some cubage perhaps, or actually this guy would be cubage on the bottom. So they really won't work out the same. So if you happen to look up the Ksp values for these guys and compare them, you would say that this guy up on top would be the most soluble, and this guy would be the least soluble. But when you actually go through the ice table calculation like we just did and do the calculation, what you actually see is the opposite. You actually see that the top guy is the least soluble. And actually this guy is the most soluble. So you cannot directly use the KSPs in a situation where they do not break apart into the same number of ions. You do actually have to do the calculation like we just did, and then compare and see which one would be more soluble, because you might be surprised, as you can see there on the right hand side of this particular table. So if they are the same number of ions, you could directly use that KSP, but if they're not, you do need to do the calculation for each one and figure out which one has a greater solubility in water. Any questions on that there? All right. So earlier I mentioned that, based on solubility rules, not everything is 100%. And there's a number of things that affect solubility. And one major thing that affects solubility is the presence of a common ion. So if you remember, we saw common ions in the last chapter when we talked about buffers. And what we saw with common ions is, in the terms of acid and bases, is they suppress the acid or base from breaking apart. Same thing sort of happens here. It actually decreases the solubility of a salt. And that again goes back to a simple explanation of how these equations are written. Solid on the left, aqueous ions on the right, which means if we have a common ion, the ion must be on which side of the equation? It has to be on the right-hand side. Le Chatelier's principle would say if you had a common ion, you're increasing that, right? Which means the equilibrium should shift away from it, right? Towards the solid side, basically keeping that guy together rather than breaking apart. And that's what we see here. The presence of a common ion will basically decrease the solubility of that salt. Based on Le Chatelier's principle, it's going to force that equilibrium to the left, and it's going to keep that guy together rather than obviously breaking apart and dissolving in solution. And we can see an example of this if we look at, if I don't overshoot it there, if we look at silver bromide, this is the KSP for silver bromide. And if we run through our calculation here and figure out the solubility here of silver bromide in water, it would be just like we did previously. We would have our silver ion and our bromide ion. Our initial here again would be 0 and 0. Change would be plus S. At equilibrium, S and S. That means our KSP here would be the silver times the bromide, which basically gives us S squared is equal to 7.7 times 10 to the minus 13. Taking the square root there, gives us a solubility of 8.8 times 10 to the minus 7 molar. Again, would be the molar solubility of silver bromide in water, basically. Any question on that calculation? Pretty much the same calculation we've been doing. Now, what would be the solubility of this guy if we put it in a solution that already contains sodium bromide? The common ion here would be the bromide, right? This guy in solution would break apart into a sodium and a bromide. That would be our common ion that we would have in this situation. We could figure it out the same way. We could start with our equation. So initially we would have 0 this guy, but because this guy is present, we would actually have an initial concentration of this guy coming from this sodium bromide. It's basically going to be supplying that. The rest of the table here will be similar, plus S, which means at equilibrium, S and 0.001 plus S. Any questions on that so far? We're going to do what we did on the other side there. We're going to solve for S. I'm going to get rid of some of that so I have somewhere to write. So for this guy here, the Ksp would equal S times 0.001 plus S equals our same Ksp of 7.7 times 10 to the minus 13. Clearly, if I distribute that S, I'm going to do a lot of math that I don't want to do. This K value is large or small? It is small. When we have a small K value, we can assume, we could assume in this case, instead of X, S is equal to 0. Just like what we do with the X is it is only the one that we're going to add to pretty much in this case. So by doing that, that gives us an S times 0.01 is equal to 7.7 times 10 to the minus 13. And clear this up a little bit. Dividing the 0.001 to the other side there gets us 7.7 to the minus 13 divided by 0.001 gets us a molar solubility of 7.7 times 10 to the minus 10 molar. Just like we do with X, you can divide that by 0.001, times it by 100, and you're nowhere even near like 1%. So most cases you're going to be good. You should still check it, but you probably will be good in these cases. What we do see is the solubility is higher. Which one? This number is higher than that number. Yes, 10 to the minus 10 is 10 places to the left with zeros. 10 to the minus 7 is only 7 places to the left with zeros. So it is much more soluble in water because the other one obviously has the common ion. The presence of this guy here is going to cause that equilibrium to shift to the left there, keeping the silver bromide together. Any questions on that one there? Okay, so why don't you try the next one, see what you come up with here. The Ksp for silver chromate is 9 times 10 to the minus 12. What would be the solubility of this compound if there was already 0.1 molar potassium chromate? Take a couple minutes, see what you come up with. Given the Ksp, so we do know this guy is going to be our solid. So that is going to be silver chromate. Going to break apart into 2 silver ions and a chromate. It's in a solution of potassium chromate, which is K2CrO4, which would break apart into obviously 2 potassiums and a chromate. Obviously here it is the chromate that is our common ion. And since the concentration of this guy is 0.1 molar, it is a 1-to-1 relationship between these two, which means this guy would also be 0.1 molar. So we'll start our ice table here, initially 0. Important though, we do have an initial concentration of this guy from that potassium chromate. Rest of the table here will be normal. We want to make sure we also include the 2 there for the coefficient and an S here, giving us 2S and 0.1 plus S. Any questions on that so far? Our Ksp expression here would be the silver. We need to also make sure we square it because of the coefficient times the chromate. Putting our numbers in gives us 2S squared times 0.1 plus S equals 9 times 10 to the minus 12. Just like I did on the previous problem here, I'm going to assume that S is equal to 0. And again, it is the one we're going to add. So that will give me 4S squared times 0.1 is equal to 9 times 10 to the minus 12. However you want to do that, you can multiply the 4 and the 0.1 together, then divide it, or divide them separately, whichever way you want to do it. And whichever way you do it there, it gets you S squared is equal to 2.25 times 10 to the minus 11. Obviously here we're going to take the square root. And if we do a little square root action there, looks like a 4.7 times 10 to the minus 6. Again, this would be our molar solubility of the whole thing in moles per liter, which obviously if we wanted grams per liter, we could use the molar mass to do that. Any questions on any of that? Obviously, as well, you could check it by dividing by 0.1 times it by 100. And again, you are good in terms of the check. Going to continue on here. So first off, any questions on what we were talking about here before we took a little break? This is, again, one of those really important things in terms of concentration and whether or not you sort of see the solid form based on solubility rules. And again, if you really don't have sort of the right concentration, you really won't see that solid form. And again, one thing that can sort of impede the solid forming is what we saw here in these last couple of things, which is a common ion. Again, it's basically Le Chatelier's principle, as we talked about, going to keep that guy together and allow it to really not break apart. Once again, the presence of this common ion causing the shift this way and really decreasing the solubility that we would see versus what we would see in water. So typically the presence of the common ion will definitely decrease that solubility. It usually things are more soluble in water, again, because there's really nothing floating around in there other than water, as opposed to obviously some ions that could cause this effect. Another really important thing that affects the solubility is actually pH. So pH can play a pretty good role in terms of affecting solubility. And especially when we're dealing with things like acid and bases, really playing with the pH or adjusting the pH can actually sometimes actually increase the solubility, but it could also decrease the solubility as well. So the presence of a common ion, as we just saw there, will decrease the solubility. When we have insoluble bases, they typically will dissolve in acidic solutions, and vice versa. If we have an insoluble acid, it typically would be more soluble in basic solutions. So if we take a guy like magnesium hydroxide, which is obviously a base, and if we kind of run through our solubility calculation like we did before, here the Ksp is 1.2 times 10 to minus 11. Borrow that So if we ran through the calculation like we did previously, we would go initially here 0 and 0. Change here would be plus S and plus 2S. Again, getting us to equilibrium of S and 2S. This going into our Ksp expression of the magnesium times the hydroxide, which again, we do need to square it because of the 2 that is there, would give us basically S times 2S squared is equal to 1.2 times 10 to the minus 11. That essentially would then become 4S cubed is equal to 1.2 times 10 to the minus 11, squaring the 2 and the S in the second one there, and then multiply it, which gives us, if we solve it here, 1.2 to the minus 11 divided by 4. And then we're going to, again, take the cube root of it. So you can do caret parentheses 1 divided by 3. If you don't got a calculator that has a cube root button. And we get something like 1.4 times 10 to the minus 4 molar. First off, any questions on that calculation there? Now, how is this important for pH? What here would be important for pH? It would be the hydroxide concentration, right? So by doing our ice table here and our KSP problem, we could actually calculate the hydroxide concentration. The hydroxide concentration here from our table would be 2 times S, which would be 2 times 1.4 times 10 to the minus 4 molar. And that gets us 2 times 1.4 to the minus 4 molar, a 2.8 times 10 to the minus 4 molar. That would allow us to calculate our POH. Which would give us a POH of 355, I believe. So this should give us a POH of 3.55. And that would obviously give us a pH of 14 minus that, giving us a 1045 in terms of the pH in this case. So one application here is you can see you can use something like KSP when you're dealing with acid or bases, do your KSP table. You could get your OH minus concentration, or you can even get your H plus concentration, which would allow you to calculate the pH of this solution. First off, any questions on this? So that is the pH here of this solution, sort of in water. It's like 10.45. It is basic like we would expect. So what happens in this solution if we decide, let us lower the pH below 10.45? So we decide we want to actually drop the pH lower than 10.45. How would I drop a pH? What would I need to add? Probably. You lower the pH by adding acid or base? Acid, right? So when we would add acid to lower our pH, we would essentially be adding H plus, which if we look at our sort of equation up here, I clean it up a little bit there. If I add H plus to this equation, what is going to happen? Will it react with anybody there? It will react with the hydroxide, right? The H plus and the hydroxide will make water. So that would be essentially doing what to the hydroxide? Adding or removing it? It would be removing, right? And Le Chatelier's principle would say, if I remove the hydroxide, the equilibrium should shift which way? should shift towards the side you removed it from, which means would it increase or decrease the solubility? On the right-hand side of the arrow, is that solid or aqueous ions? It's aqueous ions, which means it will increase the solubility. So that is what the top sentence means. If you have an insoluble base like this guy and you lower the pH, as you can see, you maybe don't even need to make it truly acidic, but by adding acid, what that will do is based on Le Chatelier's principle, it will react with the OH minus, it will form water, and that will essentially remove hydroxide from this equilibrium, causing the equilibrium to shift to the right to fix it. And the resulting of that is you will actually see your solids start to dissolve as a result of that process. Any questions on that? So it would shift to the right, more soluble. And once again here, you don't even, to be truthfully honest with you, you don't even need to get into an acidic pH. You just need to drop it below that 10.45 threshold and you will start to see it actually start to dissolve a little bit more. What would happen in the opposite case here if I decided to take the pH above 10.45? When I take the pH above 10.45, I'm going to make it more basic, right? Which means the OH minus concentration, is it going to go down or go up? Yeah, the OH minus concentration should increase, right? In order to make it basic, you're probably going to add a base, which is adding more hydroxide. So now in this situation, if I decide to take the pH above that sort of threshold of 10.45, what is going to happen in this situation is I am now going to be adding, all right, this guy. So adding. And based on Le Chatelier's principle, if I add more hydroxide, I should see the equilibrium shift away from it. So it should shift to the left here. And if it shifts to the left, is it becoming more soluble or less soluble? It is becoming less soluble. So we're basically adding more hydroxide to this, which is kind of like a common ion in this case. And it's going to shift it to the left and keep that thing together. And again, if you brought above 10.45, you would actually see a lot more solid, probably maybe dropping out of solution in that case, or the solid would actually still remain. You might see a little bit more come out, but it definitely would remain. So pH plays a really big effect in terms of solubility, especially when you're dealing with acid or bases. If you have a base, you can add some acid, and again, that's going to cause that base to really start to dissolve more. And if you have an acid, you could add base to it, which will do the same thing. Because if you had an insoluble acid, you would have H plus on the right-hand side, right? And if you added some base, it would also make water. It would remove the H plus and cause the equilibrium to shift to the right. Question on pH. So one sort of practical application of this is you could use the Ksp to really figure out sort of your baseline pH for a particular solution. And you can then know if you bring it above or below that pH, you could either increase or decrease the solubility of that particular salt. Any questions on that there? Although we don't do these experiments here anymore, there used to be a whole bunch of qualitative analysis experiments that were done in this class. And part of those experiments were basically this idea: you had a whole bunch of ions floating around in solution, and you wanted to precipitate out certain ions first and keep the other ones sort of floating around in solution. And a very common procedure that you do in those type of experiments are you play with the pH a lot. You make it acidic, you make it basic. And really what that does is it allows certain ions to sort of come out of solution at the right time, keep other ions in solution. So it's a really good practical application. If you're doing an experiment, you could almost force certain ions based on the pH to stay in solution and keep other ones to kind of come out at that particular pH. Any questions on pH and solubility? At least they agree with my pH. That's good. All right. Now, we could also look at the Q, as we talked about at the beginning of this chapter, which is that reaction quotient. And we could use that to determine whether or not we would expect a precipitation to occur. And as we talked about at the beginning there, if you calculate Q, which once again is calculated the same as the KSP, so it's calculated the exact same, not that they're equal to, but they're calculated the same way. And again, if you have a Q that is greater than the KSP, it will go towards the left-hand side, and you would expect a solid to form. And if you have Q that is less than the KSP, it would go towards the right-hand side, and you would expect no precipitation to occur at that particular point. Again, this would be more your unsaturated solution and your supersaturated solution that we talked about earlier. So let's take that one here and decide, you know, will it precipitate form? So we take our 2 milliliters, 0.2 molar sodium hydroxide, and we add it to 1 liter of 0.1 molar calcium chloride. Will we expect a precipitation to form? So one of the things you want to sort of figure out is, obviously, there's really kind of two options of products that can be made. So the sodium hydroxide is basically a source of sodium ions and hydroxide ions, right? And our calcium chloride is really a source of calcium ions and chloride ions, right? Now, in this case, it's obviously going to do some type of double displacement sort of reaction that's going to take place, which means your two options are sodium and chloride coming together, and your other option would be the calcium and the hydroxide come together. So this is where you might want to think about solubility rules and think about, you know, would either one of these guys perhaps form a solid? And the answer for sodium chloride should be no solid form there, as sodium is soluble in everything. So the other option would be the calcium and the hydroxide coming together, and that would be your really only possibility in terms of a solid that's being formed here. Any questions on that part there? So we can look up the KSP value for calcium hydroxide there in a table. And basically what we want to figure out is Q greater than the KSP? And if it is, we would expect a precipitate to form. And if Q is less than a KSP, obviously we would not expect a precipitate to form. Typically, much like what we used Q before, you would have the K value, KSP value given to you. Because really the whole point of Q is very similar to what we used it for before, is to use it to help us basically answer a question. Before, it was to help us answer, you know, are we at equilibrium, which way you need to go. Here is really to help us answer the question, should we expect a precipitate or not? So you would definitely probably have the KSP given to you, or if it's not given to you in a problem, you could look it up in a table usually. Yeah. Other questions? All right, so remember Q here is basically calculated the exact same way as our KSP, which means it would be our calcium concentration times our hydroxide concentration. And we do want this in the mixture. So really our sodium hydroxide is going to be our source of hydroxide, right? And our calcium chloride here is going to be our source of calcium. But we want to really know the concentration when we put them together. So this is again like a M1V1 equals M2V2 situation. I am going to convert this into milliliters, so I got everybody in the same unit. So I'm going to do 1,000 milliliters of that guy. So if I want the calcium concentration in the mixture, it would be our 1,000 milliliters, which is a 1 liter, times the molarity, which is like M1V1, divided by V2, which is the total volume, which is 1,000 milliliters plus 2 milliliters, which would be 1,002 milliliters. Again, 1,000 milliliters of the calcium chloride plus 2 milliliters of the sodium hydroxide gives us a grand total of 1,002 milliliters. So we're going to do 1,000 extra zero there, 0.1 divided by 1002. Going to get us a concentration for calcium of like 9.98 times 10 to the minus 2 molar. We will do the same thing here for the hydroxide. So the hydroxide, we have 2 milliliters times 0.2 molar divided once again by our total volume here. Milliliters cancel just like they do up there. And that gets us 2 times 0.2 divided by 1002. And this will give us something like 3.99 times 10 to the minus 4 molar. Any question on how to get those numbers? Okay. So now that we have those numbers, we could actually just put it into our Q. So our Q would equal our calcium, which was 9.98 times 10 to the minus 2, times our hydroxide, our 3.99 times 10 to the minus 4, and we want to make sure we square it as well. So squaring that number and timesing it by 9.98 to the minus 2 gives us a Q value of 1.6 times 10 to the minus 8. First off, any question on that calculation there? So now we have the Q value, and we also have obviously the Ksp value. So we want to compare it. In this case, Q versus the Ksp, is it greater than or less than? It is less than, right? 10 to the minus 8 is a smaller number. That means, would we get a precipitate here? We would not. So it would go towards the product side, and we would expect no precipitate to form. So this again is another important aspect of solubility. Although based on solubility rules, it tells us when we put those two things together, we should actually get a solid. But the concentration is really important of those ions that are floating around in that solution as to whether or not you'll actually see that solid form. And again, if you have the wrong concentrations, you will actually not see the solid form, which is also, again, although we don't do those experiments and those qualitative analysis experiments, a really big issue because you add a lot of reagents along the way. So you're doing a lot of dilution, and you can sometimes lower your concentration of your ion in that solution where it may not actually precipitate out when it's supposed to. And they could do some steps in an experiment to help you out. You could actually just concentrate it back down, boil off some of the water, and it becomes more concentrated, concentration increases, and then you'll actually see the solid form. Any questions on Q and Ksp? Okay. Another really important sort of our practical application of Ksp is what is sometimes referred to as selective precipitation. And selective precipitation is pretty much the basis of those experiments I've been talking about here. When you have multiple ions in solution, you may not want to precipitate out both of them together. You may want to actually precipitate out one at a time so that you can know which one's coming out at which time. For example, in this experiment here, we basically got a solution of bromide ions floating around and chloride ions floating around in the solution. And we're going to add some silver to it, you know, like silver nitrate, which is like a source of silver. Both of those things, based on solubility rules, will precipitate out. You will get a silver bromide precipitate, and you will get a silver chloride precipitate based on solubility rules. The problem with it is this is basically the picture of both of them. They are basically both white solids, which means if you do this incorrectly and you just add the silver, however you want to add it, without the right concentration, you will get all this white solid that will come out. And there's really no way for you to go, I think this white crystal is the silver chloride, I think this white crystal is the silver bromide. So it may be to your advantage to actually precipitate out one and leave the other one still floating around in the solution. And you could use Ksp to help you do that. So in this particular problem, we want to add silver, and we want to add it so that we only precipitate out silver bromide. So we want to add the silver so it will only attack the bromide and then basically precipitate out as a blue solid. No, it should be a white solid, but a blue solid there, or as the solid in this particular case. The goal here is to leave the chloride ions alone, and they're just going to be floating around still in the solution at this point. So really our two sort of Ksp things that we would deal with is silver bromide and silver chloride, which again, we could write our expression for our reaction. We also obviously can get our Ksp values from the actual table. So if we write our Ksp expression for silver bromide, the Ksp would equal the silver concentration times the bromide concentration, and that would equal 7.7 times 10 to the minus 13. Based on the question, what I know is that the bromide and the chloride ions are floating around with a concentration of 0.02 molar. So I know from the problem that that is the concentration of those ions that are floating around. What that means is if I look at my Ksp expression here, I obviously know the Ksp value, and I also know the bromide value that's in that particular solution at this point. And that is helpful because I am looking for how much silver I need to add. So if I rearrange the Ksp and actually solve for silver, the concentration of silver would be 7.7 times 10 to the minus 13 divided by the concentration of Br minus, which again, we have both of those numbers, so we could put it in. And if we do that here, we will get 7.7 to the minus 13 divided by 0.02 gives us about 3.9 times 10 to the minus 11 molar. So that number right there represents the minimum amount of silver concentration that you need to throw in there to actually start to see the silver bromide start to precipitate out. So that is the minimum concentration of silver needed to see silver bromide starting to come out. Now we could do a similar calculation for the silver chloride. And again, our Ksp here would be our silver concentration times our chloride concentration. And that would equal 1.6 times 10 to the minus 10. Solving for our silver concentration, it would be 1.6 times 10 to the minus 10 divided by our chloride concentration, which once again is the same number. So that would be 1.6 times 10 to the minus 10 divided by 0.02. This should be 8 times 10 to the minus 9. That should be 8 times 10 to the minus 9. Good. Yes. Yes. Exactly. So that's the minimum concentration that's necessary for silver bromide to come out. And again, if you added that, you should start to see the solid, and that should be silver bromide. Yeah, so truthfully, you could go anywhere with our right number there at 8 times 10 to the minus 9 on the high end there. You could go anywhere between 3.9 times 10 to the minus 11 to below 8 times 10 to the minus 9. And you can use any silver concentration you want in there, and you should see silver bromide come out. It should be enough. Yeah, so at that point, if you were doing this, you would want to keep adding it until you didn't see any more solid come out, as long as you're again below that 8 times 10 to the minus 9 number. At that point, you then could kind of increase the concentration above 8 times 10 to the minus 9. And again, that should be enough to start to get the silver chloride to come out. Again, anything below 8 times 10 to the minus 9 would be not enough silver to actually see the precipitate form. So you got to get to that sort of level. So that's how you could kind of use the concentrations, as long as you punch it in your calculator correctly there, to to your advantage, basically, to sort of selectively precipitate out ions in solution. Other questions on that? Okay. This is sort of the experiment I was talking about that we don't do anymore here. But this is what's known as qualitative analysis. And there are ions that are in different groups, group 2, group 1, 2, 3, 4, and 5. They are actually not groups off the periodic table. They are grouped together based on similar solubility sort of factors. So this is like your, you look at group 1, which are these 3 guys. That is like your chloride, bromide, iodine solubility rules, which is soluble in everything except for silver, mercury 1, and lead 2. So what we do, for example, is each of these groups have a precipitating reagent. So if you add HCl, that is a source of chloride, and chloride in those guys will precipitate these guys out as solids. It would actually leave all these other ions, if you had them all in there, still floating around in the solution. So again, it's almost selectively precipitating out just the group 1 ions. You then would go through other procedures to separate out the silver from the mercury from the lead, and you could get some positive tests for each of those ions at the end. At that point, you then could hit it with something like hydrogen sulfide gas, which is toxic, deadly, smelly, and be very happy we don't do these experiments anymore. That will precipitate out group 2. But if you look at group 3, it's actually the same reagent that's being used to precipitate out each group 2 and group 3. And what the difference is actually the pH. In group 2, it is really acidic. It's like 0.5 on the pH scale is what you need to get it down to. Very, very acidic. And that is enough to take out the group 2 ions, but leave the group 3 ions still in solution, which is what you would want at that point. Once you get the group 2 ions out of there, you then could use the same guy, but make it very, very basic. And that will allow the group 3 ions to sort of come out. So this type of qualitative analysis experiments, they use a lot of the Ksp sort of properties to help sort of selectively precipitate out things like pH, things like concentration. Those things are used a lot in these type of problems, and we don't do any of it anymore here. What also happens though is the last group there, group 4, sometimes called group 5 as well. What you're left with are things that are typically soluble in everything. So what happens when you get to the last group in this type of experiment is you got to rely upon flame test, because things like sodium is soluble in everything, potassium soluble in everything. So if you ever done a flame test, it's sometimes not the best way to solve for things because it doesn't work very well. So that is what's used there. We used to do one group here, they dumped it out. But very common in this class years and years ago, that was all you did. You should be happy you don't do it anymore. Really bad reagents, smelly reagents. But it's just a bunch of experiments where you basically just have all these ions floating around, just kind of selectively precipitate them out. Any questions on that there? All right, so last part of this chapter is involving complex ions. And a complex ion is typically a metal in the middle. A lot of times it's a transition metal that has a +2, +3 charge, and a bunch of ions or molecules that are attached to it. And those guys are what are known as ligands. And ligands are Lewis bases. So if you remember, a Lewis base is an electron donor. Yeah, so that's the guy that will give away a pair of electrons. Things that are really good Lewis bases are things that have negative charges because they've gained electrons. Also things that are polar that have non-bonding electrons, like water. Polar non-bonding electrons. Ammonia is also a really good ligand. Polar has got those non-bonding electrons. So those are really good Lewis bases. A Lewis acid, if you remember, is something that's basically electron deficient, like your metal in the middle, which has a positive charge, right? Only way for it to become positively charged is it had to lose electrons. So it is electron deficient. So this is a formation of a complex ion, which is actually this guy on this side. This is a cobalt with 4 chlorides attached to it. And we could write an equilibrium expression for this. This is what is known as Kf, and it's no different than any other equilibrium we've done before. It is our products over our reactants. We also, again, need to take the coefficient there and make sure that we take it to the fourth. As the Kf value increases, the stability of the complex ion is also increased. And that is because of the basic idea of if you have a large K value, you should have more products. And if you have more products in this type of thing, that is your complex ion. So you would have more complex ions being formed. Unlike Ksp values that we talked about, which are super small, these guys are the opposite. These guys are very, very large values for Kf. So Kf values are usually very, very large values. And that's really important for how we approach some of the calculations involving these guys. Because they are so large, it's almost assumed that it's all going in one direction towards the product side, but it's still an equilibrium that happens. By the way, ligands are added one at a time. So not all the ligands basically pop on there at once. They add one at a time, kind of similar to how H pluses are lost, and they're lost one at a time. This is both cobalt 2, but you can see the different ligands attached gives it some different properties. So one's more of a pinkish solution where water is the ligand, and our blue solution here where chloride is the ligand. So just to kind of go over that ligands and how they are added. If we take the one that we're looking at here, what would happen is the very first thing that would happen is the cobalt there would pick up basically one chloride. And you would get COCl plus 1. And you could have a K value associated with that, K1 we'll call it. The next thing that would happen is this guy that picked up one chloride would then go and pick up a second chloride, giving you COCl2, and that would have a K value associated with it. The third thing that would happen is this guy here would pick up our third chloride. And we would end up with this. And lastly, this guy here would end up picking up the fourth and final chloride. That would be K4. So a lot of times when we're dealing with these problems, we oftentimes look up the overall reaction, which you could get by this stepwise process. Remember, when we add these together, anything that's on opposite sides cancels. So that guy cancels, that guy cancels, this guy cancels. Leaves us a cobalt plus 1, 2, 3, and 4 chlorides. Gives us our complex ion that gets formed here. So again, this happens in a stepwise fashion. By the way, if I wanted to calculate the Kf, what would I get the value? How would I get it? I take all those K values and add or multiply them together. You should multiply them together. That's what we talked about with the Ks, right? You would take K1 times K2 times K3 times K4. Yeah. So that's an important thing to keep in mind. You know, sometimes in these problems, they give you just the overall reaction to look at. Sometimes they will give you sort of the individual sort of steps as each of those ligands basically attach. And again, you could use actually either one of those things and to solve a problem. They're all equilibrium reactions, which means you could use equilibrium concentrations as long as you have them for those guys. So some common ligands like water, NH3Cl minus CN, again, polar, having non-bonding electrons, also having negative charge is really helpful. Another important thing with complex ions is what's sometimes referred to as coordination number. Coordination number is the number of atoms attached to the metal that's in the middle. So when we look at cobalt with 6 waters attached, it has 6 of those waters. Each water attaches through the oxygen, which means the coordination number here would be 6. The cobalt has the 4 chlorides attached, and each attached through a chloride, which would be 4. Now, sometimes people think, well, it's just this number here. And the answer is it is not just that number there. These ligands here are what are referred to as being monodentate, which basically means they attach in one place. But there are some ligands that actually attach in multiple places per molecule. En, ethylendyl diamine, is an example of that. It looks something like this. It has the ability at both of these nitrogens to actually attach to the molecule, the metal. So, you know, if you had something like cobalt with 2 of those, the coordination number here would actually be 4, because if you had 2 of those molecules, I'll draw them both. And you put your cobalt in the middle, this nitrogen would attach, that nitrogen would attach, 2 per molecule, along with this one and this one, which means, whoops, I missed it, that one. There, the nitrogen. And that means if we look at it, what we see is 1 atom, 2 atoms, 3 atoms, and 4 atoms that are attached to it directly. So the coordination number here would be 4. So it's not always the little guy on the bottom for coordination number. It depends on the ligand. This is what is known as being a bidentate. Bi meaning 2 could attach to it. Oxalate's another example of that. Oxalate looks like this. And at each of those oxygens that carry the negative charge, they combine to a metal. So you get like a 2-for-1 situation for every oxalate that you have. There are certain ligands that can attach like in 6 places per molecule and so forth. So it's not necessarily always the little subscript that's on the bottom. It does depend on the type of ligand that's present. But a lot of ligands will attach in one place. These 2 are the common ones that will attach kind of in 2 places. You know, so you just got to keep an eye out for those things. Any questions on that there? So when we look at a problem like this, which is 0.2 moles of copper 2 sulfate is mixed with 1.2 molar ammonia, what is the concentration of copper 2 at equilibrium? I think what I'm going to do, actually, I think this is a good stopping place, and we'll pick